Hi, my name is Maya Sitaram, and this summer I worked in the Auton Lab under the mentorship of Miss Jessie Chen and Dr. Archer Dabrowski. I'll be presenting the results of my project titled Evaluation of AutoML Systems using OpenML Datasets. My project will focus on evaluating an automated machine learning tool developed by our lab against other open source AutoML tools. By validating our tool on several OpenML datasets, we can identify the unknown challenges and opportunities for future research into improving our system. We can also compare our performance to that of other AutoML tools across different problem applications. First, I would like to introduce automated machine learning and its differences to machine learning. Existent methods of building a machine learning system to solve real-world data problems require collaboration between problem domain experts and data scientists. Since there is not a single best ML model, every application requires a manual process of data cleaning, featurization, hyperparameter tuning, and model selection. Automated machine learning AutoML, however, handles these processes automatically, assembling the optimal pipeline or sequence of primitive algorithms and machine learning steps to transform the input data into target values. This enables domain experts and data scientists to focus on the underlying problem construction and quickly prototype solutions to new problems. Our lab participates in the DARPA Data-Driven Discovery of Models D3M program, and as a part of the program, we have developed our own AutoML tool named AutonML, which has outperformed other competing D3M AutoML frameworks in periodic DARPA evaluations. However, our system has not yet been evaluated against non-D3M open-source AutoML systems, such as Auto-Sklearn, H2O AutoML, and TPOT, and this is the primary motivation of our experiments. The following is the programming structure of our automated evaluation framework. We operate on an 8-core Linux machine and evaluate 76 OpenML datasets of binary classification tasks. And each dataset is randomly split into training and test datasets, and we pass the identical test-train split to each AutoML framework as inputs. Pipeline search and fitting are executed under 3 training time limits of 1 minute, 10 minutes, and 20 minutes. From each AutoML system, we collect the predicted labels from the top pipeline, which achieves the highest area under the ROC curve or AUC score on the training data. From AutonML specifically, we will also collect predicted labels from the best pipeline, which achieves the highest AUC score on the test data predictions. In the analysis of our results, we pose research questions such as how significantly AutonML outperforms others in general. To answer this, we use relative performance metrics such as lift, which compares the accuracy of predictions made by each AutoML pipeline to that of a majority vote baseline model. We also use an AUC score metric. For each data task, we compare the AUC scores of the pipelines evaluated and rank the pipelines between 1 to 5. Finally, we wish to understand the types of datasets that AutonML outperforms other frameworks and the datasets that AutonML fails to beat others. We answer these questions by using datasets with varying metafeatures and determining whether the input space to each AutoML influences its performance. In the following plots, we denote AutoML's best pipeline with the highest AUC scores on the test data in purple. We also denote AutoML's top pipeline with the highest AUC scores on the training data in red. We plotted accuracy-based lift in the upper graph and AUC-based rank in the lower graph per increasing training time limit. The best pipeline of AutonML ranks first or has the highest AUC score among the frameworks evaluated. Its lead in performance is consistent regardless of training time limit and significant despite accounting for error. The best pipeline also has the greatest lift or the greatest accuracy compared to the lift metrics of other frameworks. This lead is also consistent per training time limit, though it is not significant. Unusually, we find that the top pipeline has poor predictive performance as it has the lowest rank and the lowest lift. To identify any discrepancies in the testing and training performance per AutoML, we plot accuracy-based lift on the test data predictions versus lift on the training data predictions in the upper graph. A line at y equals x is drawn to denote identical performance in either dataset. We create a similar graph below for AUC-based rank. We expect the AutoML systems to perform better on the training dataset and comparatively poorer on the unseen test dataset. However, the top and the best AutoML pipelines perform unexpectedly and achieve greater lift and higher rank on the test dataset than on the training dataset. Finally, we identified the types of datasets that our AutoML performs poorly and the datasets that our AutoML performs well. We plot accuracy-based lift from both the top and best AutonML pipelines per increasing number of columns of the input dataset above. We also plot the rank of the pipelines from all AutoML systems per increasing number of columns of the input dataset below. Unexpectedly, we perform worse on lower dimensionality datasets with fewer columns, as for a few datasets our lift is below 1 and we perform more poorly than a majority class or baseline classifier. By visual inspection of the second plot, however, AutonML's best pipeline ranks first for lower dimensionality datasets. As seen in the previous slide, performance does not have a clear linear relationship to the shape of the input dataset. Our next steps would be formulating a classification task to predict the performance given the meta features of a dataset and identify a potential nonlinear relationship between these variables. Furthermore, in future work, we must review our training evaluation to ensure that the best pipeline for prediction is the top pipeline found during training. In addition, we must identify the source of discrepancies between performance on training data and performance on test data within our AutoML system. In conclusion, I would like to thank the RISS program organizers, Ms. Rachel Burson and Dr. John Dolan, and my mentors, Ms. Jessie Chen and Dr. Artur Dabrowski, for providing me this opportunity and supporting me in my research journey.